Alright, so let's quickly look at how we went from the perceptron to multi-layer perceptron and in the end a neural network. Yeah? They all mean the same, roughly, but I just want to touch upon some nuances. Yeah? Here is a perceptron. Yeah? We know that the output here, the output is linear, is x0, w0, yeah, plus x1, w1, plus x2, w2. Output is linear, so you know that there is a need for nonlinearity as a result of Minsky and Paper's book. So the first idea was to add a hidden layer. Yeah? Because a XOR port is actually an AND port and an OR port together. Yeah? But here we can quickly calculate what the output would be. So let me calculate the output, and let's call it O1 here. Is actually x1 with the weight w11 and is x2 with the weight w21. Yeah? So it's x1 w11 plus x2 w21. Yeah? 21 is this arrow, 11 is this one. And the output of 2, O2, yeah, equals x1 times w12, x1 times w12 plus x2 w22. Okay, now what is the output here? Well, it's w1 O1 plus w2 O2. And what is the big conclusion? Well, the big conclusion is that the output is still linear. We've not added nonlinearity just because we add a layer in the middle. Doesn't mean that adding a layer in the middle has no value. It does have value, but it does not give you the nonlinearity. So that's how we get to a neural network, although these two basically mean the same thing. When you add an activation function, and this is a red piece, to a multi-layer perceptron or a neural net, that's where you get the nonlinearity. So the activation function gives you the nonlinearity. Here we go. What are activation functions? Well, we've seen a few. We've seen the sigmoid function. Remember, it's that curve we used in logistic regression, for example. Yeah. This curve is smooth, is continuous, and is differentiable. Yeah, differentiable is important because we will using backpropagation, and backpropagation uses gradients. Yeah, so the function need to be differentiable. So it's a little bit. I can draw it a little bit better, like this. Here you go. So sigmoid will be used for binary classification. Okay? Binary classification. Now what is not so good about the sigmoid? Well, not so good is this piece here and this piece here. Yeah? The curve is rather flat and your gradients will disappear, because the gradient on a horizontal line is 0. So not used that often anymore. Then we have another activation function which we call softmax. What sigmoid does well is it converts a linear score to a probability. So here on the x-axis you have your linear score, and then when you look at the y, you will find the score here, and if the score is bigger than 0.5, because this is half here is then 0.5, then you give it a 1. If it's below 0.5, you give it a 0. We've seen that as well. Softmax is for a multi-class. And what softmax does, it converts a linear score not to a probability, because we have more than one class, but to a probability distribution. So it converts a linear score to a probability distribution. We will be using a lot of softmax. Yeah. Then the last one is called ReLU, rectified linear unit. Is very popular, and there the function. So this is your z-axis, this is your y-axis. The function goes like this. It's like this. Yeah. So you can immediately see here you have still a gradient issue, like this one, but on the positive side it has disappeared. So definitely here this one is better. Why? Because you have a constant gradient. Gradient is constant. Yeah. Nice mathematically. Yeah. So the function here is y equals the maximum of 0 and z. Yeah. So if z is negative, y is 0, and if z is positive, y equals z. Yeah. So ReLU is very popular, and we will use it a lot. Alright, so this should give you an idea on terminology. Important for you is to know that we need an activation function in order to create the nonlinearity for neural nets. And here we just gave you a few options in terms of activation function, of which I would say ReLU and softmax are the ones you need to remember.